What we're going to talk about today is a sort of different approach to doing, in particular, vector calculus, based off something called the Fréchet derivative. And vector calculus is something that is at the center of machine learning. So for one, it's how we get our exact solutions for linear regression. If you've ever done the normal equations in a stats class to figure out what the values of the weights are for your parameters in linear regression, people use vector calculus to come up with that answer. When we calculate eigenvectors and eigenvalues, we're using methods from vector calculus to determine what algorithms will work and how well they will work. But maybe a little bit less basic and more central to the contemporary deep learning methods, gradient descent is based off of gradients, which are derivatives of functions that take in vectors. Backpropagation as an algorithm, it uses a whole bunch of different ideas from vector calculus. These are really core ideas in deep learning, but vector calculus is something, it's essentially the same thing as what people would call multivariable calculus in at least the American high school system. It's something that people have a lot of sort of like fear of or dislike for. And I think the reason why is that vector calculus combines two things that people are a little sketchy on: linear algebra and calculus. And part of the reason why people are sketchy about linear algebra and calculus is that people explain both of those things the wrong way. You'll hear people say that linear algebra is an algebra for solving equations with vectors and matrices instead of just numbers. And they'll say that calculus is the study of methods for mathematically representing rates of change and areas. And while these are definitely true statements and they give deep insight to these two mathematical disciplines, they're not really the right way to think about either of these things when it comes to doing machine learning. The former uses a lot of intuition that people develop as pure mathematicians, and the latter uses a lot of intuition that people develop as physicists or engineers. But most people doing machine learning aren't either of those things. Maybe one of the common toolkits is more software engineering than hardware engineering, signal processing, things like that. And so there are better ways to understand these two general mathematical ideas that make use of concepts that are more close to the wheelhouses of folks who are doing doing software development and software engineering every day. So linear algebra can be thought of as the study of functions that can be represented by arrays. And these functions are also known as linear maps. So at the last deep learning salon, I talked about this approach to linear algebra. So there's a link there to the video on that. So the question is there a better way to understand calculus in the same way? And the answer is yes. If we think of calculus, and in particular the derivative calculus, which is what we mostly need for machine learning, it's really about methods for linearly approximating functions. So there's this deep connection between what happens in linear algebra and what happens in calculus that isn't really taught when people especially when people teach single variable calculus, but sort of unifies this two sets of ideas and connects to things that we end up using all over the place in in machine learning and deep learning. So the way that we're gonna approach this by actually defining the derivative in a different way. And that's going to end up making our vector calculus easier. So the name of this style of defining the derivative is called the Fréchet derivative, after a French mathematician who invented it. And while it's only going to give us it's going to give us the same answers as what we learned in our calculus classes, but it's going to give us a new way of thinking. And there are three major benefits to thinking this way. One is that we're going to end up with a single sort of style, a single definition, a single method of like proof and of understanding that works for gradients of single variable, vector, and even matrix functions. And even better, this extends all the way into the heady realms of functional calculus. It's not where we'll be going today, but it's cool to know that this single idea can go from the kinds of calculus that one can learn as a high school student up to the sort of most complicated kinds of calculus you can do. In many problems, and this was where I got the title for my talk, all the indices disappear from our calculations. We no longer have to juggle lots of i's and j's and k's telling us which part of which matrix or which vector belongs to which component of the gradient or the derivative. Everything will be done in a completely index-free manner. It's less cluttered, It's easier to follow. It shortens things. And for me, it's just simpler. And then lastly, we're going to end up using the little o notation instead of limits, which is sort of akin to the big O notation from computer science. And this is something that maybe people have a bit better intuition about from having had to understand some of these things about how quickly certain algorithms run. So Hans talk had some big O statements about how long algorithms would take, but none of the talks so far have included limits, if that gives you a sense for which of these kinds of things are more common in the toolkits and the practice of machine learning and software engineering. So we're going to spend most of our time talking just about how this gives us a way to do calculus on single variable functions. But we will, in the end, sort of point to how it gets used for vector calculus. And basically, this talk is kind of a teaser for this sequence of blog posts where I go through how to actually use this set of techniques line by line, every single manipulation, like carefully explained. And so if you want to get that, you'll have to check out that sequence of blog posts. I didn't want to be doing math in front of people for half an hour. So the links for that will be at the end. So single variable function, what I mean by that, when we do calculus, we're typically thinking about functions that take in and put out real numbers. But real numbers aren't real, at least for computers. There's no real numbers inside computers. So anytime that I say anything about real numbers, you might substitute floating point numbers instead. So we're thinking about functions that take in one single floating point number and put out another one. So squaring, adding to, multiplying by 5, these are all the kinds of functions that we might be thinking about. So the standard definition of a derivative that one learns in a calculus class is that the derivative is the limit of a certain ratio. So it's the ratio between the change in output and the change in input as the change in input gets smaller. So that limit there means make this change smaller, make this epsilon value go to 0. And we say that the limit of that ratio is the derivative. So we're specifically defining the derivative at a point by means of a limit. And I don't know about you, but when I took calculus classes, that was basically the moment for me when I lost track of math. It took me a long time to sort of come back around and get back to understanding and enjoying math the way I did before calculus. And so I have a preference for doing things with as few limits involved as possible. So the Fréchet definition gives you the same results, but it centers the concepts of approximation and linearity rather than limits and ratios. So what the Fréchet definition says is that if the change in the value of the output at a point epsilon away is some function of x times epsilon plus something smaller, we call that function the derivative. So what's weird about this definition is that the thing we're defining isn't alone on one side of the equation the way we normally do. So it's this sort of operational definition rather than a definition just in the usual sense. And the second thing that's sort of different about this definition is that instead of the limits appearing explicitly, we've sort of hidden them away in this last little term highlighted in purple, the little o of epsilon. We'll talk a lot about what exactly that term means, but the nice thing is that very, sort of loosely and intuitively, it just means something smaller than epsilon. And so all the gnarliness with limits, all the complexities of calculating those things gets sort of stuffed away inside this little o. And we do most of our work in calculating our gradients, our derivatives, by just doing a little bit of regular old algebra or linear algebra on all the rest of the stuff. So finally, that's the centering of approximation. The other thing is that what we have here is an equation for a line. So the other way of sort of stating that definition is that if I can always approximate the behavior of f near x with a line passing through f of x with slope f prime of x, we call the function that gives us the slope the derivative. So this our approximation of our function f, which could be wobbling and wiggling all over the place. It could be sine of x or cosine of x. It could be something, something exotic like the loss function of a neural network. But we're always going to pretend that it's just a line and say we're going to approximate it with a line, and we want the sort of best line to approximate it. And the slope of that line is what we call the derivative. So the key ideas are that we're going to approximate the function, and that the way we're going to do it is with a line. And these are basically the important ideas about derivatives for machine learning, especially deep learning. So say, like, I just want to update my model's parameters in order to make it perform better. We have all learned lots of ways to do that, but, you know, let's pretend a brief tabula rasa, veil of ignorance moment. How do I do that? One way is that I could choose my new parameters such that my best linear guess says that the performance will be better, right? So it's really hard to know what the loss is going to be at tens of thousands of values of the parameters, right? Like it can be expensive. Han was pointing out that evaluating the loss for a transformer network can pretty quickly get you out of memory errors. So what we're going to do is that we're going to try and come up with a best linear guess that tells us how the function is going to behave at a different point. And that's what we're going to use to update our parameters. It's not going to be perfect. And in fact, we know that as we move further and further away, it gets worse. That's another thing that this little o of epsilon tells us. It says that the gap between these two things is going to get bigger at about the same rate that that value epsilon gets bigger. So we don't want to change it too much. That's the last piece that that we can read off from this equation. And this leads us directly to gradient descent. Gradient descent says that our new parameters on the left-hand side of that assignment arrow at the bottom are equal to our previous parameters plus some small number times that linear approximation, evaluated at our current value of the parameters. So what we want to use our definition for is to figure out from knowledge of what a function is, we want to know what is that function's derivative. So the way we do it is we write out the left-hand side of our definition for the function we're interested in. So the left-hand side of our function definition was f of x plus epsilon. So if we consider the function x squared, we would just be writing out x plus epsilon squared. And x plus epsilon squared, that's that's a binomial, right? If I were to multiply that out, it's x plus epsilon times x plus epsilon. And so what we'll get out of that is we'll get an x squared and an epsilon squared, and then we'll get one x times epsilon and one epsilon times x, right? So first, outer, inner, last is how people talk about it in the American school system. So combining those two x times epsilons, what we see is that x plus epsilon squared is equal to x squared plus 2x epsilon plus epsilon squared. And then the next step is that we pattern match the right-hand sides. So pattern matching is something that people are maybe more comfortable doing with from computer science, from programming. Functional programming languages elevate pattern matching to actually sort of the way some functions are defined. So pattern matching is a sort of key skill in computer science. So we pattern match our two right-hand sides. So down here, I've got f of x plus something that's a function of x times epsilon plus something that's smaller than epsilon. And those are exactly the three terms in that equation at the top. X squared plus 2x, that's a function of x, times epsilon, plus epsilon squared. And for small things, something squared is smaller than something. So if I'm less than 1, then squaring makes me smaller. So epsilon squared is also something smaller than epsilon, so little o of epsilon. So now that tells us that the derivative of x squared is 2x. So far, so simple, like x squared, that's a function lots of people don't have that much trouble understanding the derivative of. So we'll see in a little bit that this same pattern matching technique also applies when it comes to vector calculus. And in that case, it's much easier to do. So I want to talk a little bit about this little o term. and what it means, in part because hopefully this will help build your intuition and understanding for big O. Pretty often when I have to think about what big O really means, I have to go back to Wikipedia, back to a whiteboard, think about it for a while. So hopefully this will help speed that process up the next time you have to do that. So effectively, a term is little o of epsilon if it gets smaller much faster than epsilon does. It's like a fancy notion of what it means to be less than, right? One number is less than another number, pretty easy to figure out. This is a way of talking about how one function is in some sense less than another function. So the technical definition is right there in the middle of the slide. If, as x gets small, the ratio of these two functions goes to 0, then we can replace f of x with little o of g of x, which says f of x is less than g of x in this sense. This means that for a small enough epsilon, anything little o of epsilon can be safely ignored. So this is what we mean when we say that this derivative allows us to approximate the original function. And so this is pretty close to the core idea of what limits were used for in the definition of the derivative, but now we've sort of separated it out from the part where we calculate the derivative and put this on just the part where we figure out how bad our approximation is. And that's a really nice sort of separation of concerns. It's a way of abstracting away how bad our approximation is. So here's a couple of examples. 0 is going to be smaller than x. X squared is smaller than x. And any number times x squared is also smaller than x. So what that means is anytime we see any of these terms, anything that looks like this in an equation that we're writing, we can replace it with little o of x and continue. So some terms that are not o of x, 1, that's something that doesn't get smaller at all. And so it doesn't get smaller faster than x gets smaller. X does not get smaller faster than x because they're the same. So the ratio of those two things is always 1. And so that's a term that's not little o of x. If I multiply x by something, the ratio of kx and x is going to be k. That's also not 0, and so that term is not o of x. So there's lots of rules for manipulating these terms, and I find them a lot easier to remember and to use than the whole cavalcade of complicated rules for calculating limits. So we sort of pack away all of those rules into a sort of like calculation strategy for working with little o terms, and it pays a lot of dividends. It makes a lot of derivative calculations much easier. So it's similar in spirit to big O, right? So big O notation from computer science lets us talk about how fast algorithms are while abstracting away any irrelevant details. So for example, maybe we've got n data values and we want to check if a query is one of them. If the data is in a list, searching it will take time proportional to the length. On the other hand, if the data is in a binary tree, famously, searching it will take time proportional to the logarithm n in order to find the data. So if what we want to do with our data is search it, a binary tree is better because O log n is faster than O n. Now, there's lots and lots of important details when it comes to actually implementing these algorithms to figuring out exactly how fast each one is. But just generally, if we're working with a really big number, we know that the thing that is O log n is almost always going to be smaller than the thing that is O n. So it saves us a lot of effort and work and cognitive load to use this big O notation to think about things rather than trying to calculate the exact speeds and the exact number of operations that something takes. So it lets us abstract away those irrelevant details and talk about which algorithm is fastest, avoiding really specifying them. Similarly, little o lets us talk about the best linear approximation while abstracting away exactly how good or bad that approximation is, because that's often a lot harder to really understand. I can say that this thing is best without knowing how much better it is than other choices, or how much worse it is than the best possible choice. So if you want to read more about these, the sort of general term for all these ways of turning limits into these simpler expressions, they're called Landau symbols. So I would definitely check that out. There's lots of good tutorial material online about them. Okay, So now that we understand how this Fréchet style of derivative lets us do the kinds of derivatives one does in an AB or BC sort of intro calculus class, we now apply them to functions of vectors. And we can define the gradient in exactly the same way. So when I say that something is a function of a vector, for folks who do pure math, I'm talking about something that takes in an element of Rn, a real valued vector, and returns a real value. And then the gradient is a function that takes in a vector and spits back out a vector. But for folks who are doing machine learning, what I'm thinking of is a function that takes in an array of floats and returns a single float. And then the gradient is something that takes in an array of floats and returns an array of floats of the same shape. So again, the Fréchet definition is going to center approximation and linearity. And what it says is that if the change in the value of the output at a point epsilon away is now the inner product of some function of x with epsilon plus something smaller, we call that function the gradient. We could call it the vector derivative or just the derivative, but people like to call it the gradient, especially in machine learning. So the only real difference between this definition and the first one is that instead of taking the slope or the value of the derivative and multiplying it by epsilon, we're taking this inner product or dot product or scalar product, depending on your discipline, between those two things. So this inner product can be written many, many ways. I think the most important alternative way to write the linear product is in terms of matrix multiplication. So when we write it that way, instead of writing those two angled brackets, we write vector transpose other vector. So the gradient is a vector, epsilon is a vector, and the way we multiply one vector with another is by taking the transpose of one and then doing matrix multiplication between the two of them. So the important things to note are that this reduces to the derivative for vectors of length 1, right? So this inner product here, this vector transpose vector, is the sum of the products of the elements of the vectors. Go into each, do like a little for loop over each vector, the vectors zip together and multiply those values. So if there's only one thing, then it's just multiply the two values together. And that's exactly what we did when we did the scalar valued derivative. So this is basically the same definition, but now we've gone up one level and defined it in a way that works for both vectors and scalars. And then, sorry, I think I didn't mention, scalar is the term people use in linear algebra for just a single number. The second term in this guy, the gradient transpose epsilon, that's a linear function of epsilon for a fixed x. So what I'm doing is I'm just multiplying these things and adding them together. That function is always going to be linear. It defines effectively a plane or a hyperplane, which is the higher dimensional equivalent of a line. So this is just like how we had the notion of the derivative as a line in one dimensions. We have the notion of a derivative as like a plane or a hyperplane, a linear function that approximates the original function. So here's how we end up using our definition. It looks exactly the same way that the way we used our definition for the scalar derivative looked. So if we want to know what the derivative of the L2 norm, the squared norm, people use this for regularization in machine learning. Gradients get calculated on it. Maybe you wondered what that gradient was. What we do is we multiply it out. The squared norm looks just like that x plus epsilon squared that we had before. We get one term that's the squared norm of x, another term that's the squared norm of epsilon, and then a term in the middle that's basically 2 times x times epsilon. So when we do things this way, the connections between scalar calculus, vector calculus, and calculus with matrices become really, really clear because we're using the sort of like same symbols and same tools for all of our, for each one of these I don't know, subcategories, subdisciplines of calculus. And again, we just pattern match the right-hand sides. So we look to make sure that there's one term that looks like the original function, blue. There's one term that looks smaller than epsilon, so that's norm of is smaller than the norm of epsilon. So norm of epsilon squared. Again, squaring makes things smaller. So that the guy in purple is our little o of norm epsilon term. And then the middle term, that's the term that gives us our gradient. So it says that the gradient of the squared norm is 2x. Notice that there's a transpose built into that middle term, so we drop the transpose when we decide what the vector is. It's really easy to see with vectors because the gradient needs to be the same shape as the inputs, or else we couldn't add them together when doing gradient descent. But with matrices, that's an important one that you're going to need to watch out for. The other little gotcha is that people often like to just write little o of epsilon without the two straight lines around it that indicate the norm, just as a notational convenience when writing little o stuff. So when you go out there and look for other people using the Fréchet derivative style, you might notice that they do that a little bit differently than what I do here. So lastly, we can use this to do derivatives of functions of matrices, and the definition is exactly the same. And this is, I think, the real killer app for the Fréchet derivative. I've found that every other approach just falls apart, gets much more complicated, really difficult to follow when it comes to functions of matrices. And I really suffered through trying to calculate derivatives for things like linear regression, when these should be things that we can do pretty quickly and easily, and the Fréchet derivative lets us do that. So it's literally the exact same definition, but now with capital letters, because people like to use capital letters when they're working with matrices. So again, we look at the value at a point epsilon away. Capital epsilon looks like an E. Sorry, I didn't come up with the Greek language. But so if we look at the value at a point epsilon away, it's now the inner product of some function of x with E plus something smaller. And again, we call that function the gradient. So the only thing that's different here is we now need to know how to do an inner product and calculate a norm of a matrix, which maybe people are a little bit less familiar with than they are with inner products of matrices, or sorry, of vectors, right? The inner product of vectors already showed up actually in Hans' talk, right, with that cosine similarity. The cosine similarity is just the normalized version of the dot product. So what is the inner product of two matrices? What is the norm of a matrix? So there's this particular definition in terms of traces that you can find if you look online. But the way to get that definition that I really like is that actually the inner product of two matrices is just turn each matrix into a vector and then calculate that inner product. So that's this last line here. It says vectorize x. That's literally like flatten, right, in NumPy or in TensorFlow or whatever your favorite tensor library is. Just flatten them out and then do the dot product between those two. It blows my mind that this actually works and gives you a really good answer for what it means to do the inner product of two matrices, but that's how it's done. It turns out that the way that's easier to work with when we're doing our algebra, when we're calculating stuff with the Fréchet derivative, is this thing in terms of the trace. If you want more details about how we calculate matrix-valued derivatives and how we understand what this sort of maybe arcane and strange trace-based expression for the inner product is, check out the blog post that is linked in the corner of this slide and should show up in the chat about sort of why this is such a sensible way to calculate the lengths of matrices. It turns out to be really closely related to things like PCA. So I don't have an example of calculating a matrix-valued derivative because, you know, maybe you should always leave people wanting a little bit more. So if you want to see how to do it and get some really cool examples, you'll need to check out the series of blog posts. But hopefully I've convinced you that these benefits are there and are real for thinking of vector and matrix calculus in terms of the Fréchet derivative. That we can write one definition, one single sort of style of doing calculations that works for gradients of all kinds of functions. That you'll notice that basically indices disappeared. I used a few in calculating those inner products, but that was just to define those things. No need to use any indices at all. And we kept the limits to a minimum by hiding them essentially inside our little o notation. So those are, I think, the sort of three big benefits of using this Fréchet derivative style. So the blog post series is linked at the top there. So there's sort of 3+1 blog posts. I had initially intended to write just this linear regression one and one on deep linear neural networks, which are really near and dear to my heart. Neural networks with no nonlinearities. They're nice because you can do math on them, even though they can't solve ImageNet or anything like that. But then while I was writing this blog post, literally in the middle of it, I came across another example, just coincidentally, where calculating the derivative of the determinant, it turns out to be much, much easier in this way. And it's something that you do sometimes have to calculate. I have another blog post on Gaussians as exponential families. This is an idea that was bigger in vogue when people liked graphical models and things like that. But there's Gaussians, the normal distribution, multivariate normals, have this really, really elegant connection to information geometry and these very cool, heady ideas. But the way that this connection is often presented is really hard to follow because there's a lot of vector calculus. So I went ahead and calculated these things in the Fréchet style because I couldn't find anybody else doing it that way, and found that it just compressed things so much shorter, so much easier to write down. And it really emphasized what was important and unique in that case, and not all the machinery and mechanics of calculating these gradients. And also a shout out to Terry Tao's blog. Terry Tao's one of the greatest living mathematicians. And if you need another endorsement for using the Fréchet derivative, that's the style he does in almost all of his calculations of derivatives and gradients and things. So that's where I first came across this style. And it's made doing calculus for neural networks, for linear algebra, for lots of things that I'm interested in just so much easier. And it's really deepened my understanding of both linear algebra and calculus. So that's all I have. Hopefully there are questions, but if not, if you can't think of any questions now, feel free to hit me up via email or on Twitter. Thanks a lot.
Thank you, Charles. That made me hate calculus a lot less, or a little bit less, if I'm being honest. So thank you for that. We have a few questions. So Rishav really liked your talk. He said, beautiful talk. He was wondering if you have any other recommendations to go deeper into these topics in the way that you're teaching. And I posted all of the links from your slides in the chat already, but do you have any more?
Yeah, so I think there are links in those blog posts to other places where I had come across these ideas. I don't have them immediately on the top of my head. So I guess, yeah, Rishav, if you could just send me your email, I'll make sure to contact you specifically with some additional resources once I have a chance to look at it.
Cool. And then someone asked, are lambdas the same as functional calculus?
Lambda is the same as functional calculus. So you're talking, I'm guessing that this is about the lambda calculus as a model of computation. So if you wanted to do calculus on lambda expressions, you would need to do functional calculus, but lambda calculus and functional calculus are different things.
And then the last question, someone asked, when is Fréchet's method applied in practice? Does it give the exact same results as the traditional methods? And how can you verify this?
Yeah, so it gives the results are exactly the same for anything except functional calculus, basically. Once you get to functional calculus, it turns out that you need a little bit of extra machinery, and there's the Fréchet derivative and the Gatto derivative are the two ways people do it, and those give slightly different answers. You could prove that they give you the same answer, so that that would be something you'd have to go about doing. And I would say it's used. I've found that a lot of people who are doing stuff like developing automatic differentiation libraries use an approach much closer to this one than the traditional calculus approach. So one person would be Michael Betancourt, who does STAN, which is a Bayesian inference library that also has automatic differentiation, just like TensorFlow. And his style is a little bit different than this one, but it also centers approximation, linearity, things like that. So I don't know if he would explicitly say he does the Fréchet derivative, but it's the same set of ideas.
Cool.
I saw actually a question about from Bodeon asking, shouldn't it be little o of epsilon squared? And this is actually an interesting point. So I didn't get a chance to mention this, but little o is kind of like a less than sign. And people are usually used to working with big O, which is like a less than or equal to sign. And so with little o, the powers are a little bit different than they are with big O. So if you were surprised that it wasn't an epsilon squared because you're used to that way of writing Taylor expansions, then that's the reason why, because there is this tiny difference. And I just slightly prefer it, but you could do the whole thing with big O instead.